Bioenergy Center, and Dr. Swarnalata also mentioned about NSF Bioenergy. So this center, I was the research director of this. So this is very interdisciplinary. So we have an agricultural, the department. So they focused on the gasification and the pyrolysis. And once you get the syngas is nothing but mixture of CO and hydrogen. Then, you do the Fischer-Tropsch process, and I'll take you through that. And also we did steam reforming. This is steam reforming of bio-derived alcohols and how you convert that into hydrogen. Because hydrogen is a big thing, as you have heard throughout this conference. And so we are trying to produce the hydrogen which will go into the fuel cells. And so therefore, we interacted with the chemical engineers who could do the separation using membrane. Okay? And so this is the thrust 2. Unfortunately, this light is not working, or is maybe too bright. Is it possible to dim the light at the stage? Can you dim the light a little bit at the stage? Maybe then I can show this, because I know it is working, the red sign. But no, I think the light is too bright. Oh, this is smart. Yeah. I know. Do you have any sticker or any other thing? Oh, this is LED. I didn't realize it. Yeah. No, you don't have any other pointer? I can do the. That's all right. I'll continue. So here, so the thrust 3, these are 3 thrust areas. So they focused on primarily on the. You know what? I have a pen, so I can use this. Okay. So here, and you can see the thrust 3. You were just trying to process this hydrogen, which goes into the fuel cells, and so this is the 3 thrust areas. They are all interconnected, and one of the big things about NSF Center is education and outreach. So, and they need to be all connected. So here, students always get confused. What is the connection? Because people always ask this question. So you see, you can make syngas from the coal, biomass, all these feedstocks, and then if I press this, you see, this is the thrust area 1, and you see the gasification and pyrolysis, and then either you get the syngas, and once you get the syngas, then you see we go to the thrust area 2, which I primarily focused, and here you see you have the syngas, which is nothing but the CO and hydrogen, and then you make the fuels and chemicals. Of course, you make the transportation fuels, and then you see that this is the thrust 2, and now if I go to the thrust 3, which I showed you earlier, then you are separating the hydrogen and purifying it, and this is the PEM fuel cell applications. Okay, so this is, you see that all 3 are connected, and then you can see that the thrust area 1 and 2 and 3. Now, so again, Fischer-Tropsch synthesis involves the syngas that you can also get from other sources like biogas, which you are more familiar with, like methane and CO2. By reforming, you can make the syngas, the CO and hydrogen, okay? And you can, of course, get from coal and natural gas as well. So there are different routes to make the starting mixture, like the syngas. And once you have that, then you can do the Fischer-Tropsch synthesis you get the reactor catalyst and the hydrocarbons, and you can make the other product. And the Fischer and Tropsch synthesis goes back to 1920s. And actually, Germany survived using coal in those days through the Fischer-Tropsch synthesis. Okay, it was basically invented in Germany. So again, I will go back to this. So you have the CO and the hydrogen, and you are making hydrocarbons, okay, and water. But if you can play the trick, you can make olefins as well. and then you can make the polymers from them. So these are all the products. Now you see, okay, now those of you who are not familiar, the way Fischer-Tropsch synthesis is done, you actually have different kind of columns. This is a little bit of chemical engineering, and bubble column, the slurry column, and then you can see the circulating and the fluidized bed reactors. Okay, and most of the time, you will see in literature when you read, is the silica, alumina, titania, and zirconia. Those are the supports, and the metals, as you can see on the right-hand corner, you see up that iron, cobalt, nickel, and ruthenium. Those are the typical catalysts that we use. Okay, and those of you may or may not be familiar with, the original Fischer-Tropsch synthesis was developed at 1 atmosphere. Okay, so but nowadays we all do it at high pressure because you want to get liquid fuels and do that. Okay, now this slide shows that this is a project we did in collaboration with UNC Chapel Hill and NC State. We are all part of the UNC system. So there, because North Carolina has lots of hogs, so there's a lot of bio-waste, and so biogas can be then reformed to make the syngas, and once you get the syngas, right, then you can make all these products. So here you see the reforming is actually a very endothermic process. But if you can use solar panels, solar system, you can then actually heat it up, and then you can do this syngas. And the idea is that we use microfluidic or microchannel microreactors, many of these, and then you can make the liquid fuels. So it's basically on-site production of liquid fuels all the way from the bio-waste or animal waste. So that is the strategy that we do. So in other words, you can apply these things in so many ways, and you can do that. Now, what is microfluidic or microchannel microreactor? Okay, so this is, those of you who are not really familiar, so if you think about a cube, okay, cube has, let's say, side A, then if you have surface area is 6a square, right? Now suppose you break the cube into small cubes, right? Then you will have so many cubes, and each one will have the 6, whatever the side length is, you will have much more surface. And this is what we apply in catalysis. Larger surface area, then you will have more reaction. For example, if you take lycopodium powder versus lycopodium solid, and you try to put it in the fire, of course you know that it is the powder which is going to burn more easily, right? So this is the same idea. Higher surface area, more catalysis, more reaction. So this is the idea, and so this is where I started when I moved from industry to academia through Purdue. So I was not trained as a chemical engineer. I'm really a chemist. So I had to learn how to do all this, or how you figure out. And so this is these microfluidic channels, and you see that the beautiful thing about this, those of you who are more familiar with thermodynamics, and you see that it's a very good heat and mass transfer. And so this is why this is really ideal, and the process safety, because you see it's a very tiny reactor. So if you blow up, nothing will happen. So it's a very good tool to really educate or to understand the metal catalyst support interactions. And that this is the easy transportation, and it's ideal for very exothermic reaction. The Fischer-Tropsch reaction is very exothermic. Okay, so you have to control the reaction, otherwise it will run away if you are doing it in a plant. And so that this is you can control the reaction parameters, and of course the numbering up. This is what I was saying earlier, the paradigm shift. So if you have thousands of these, then you can make the products using this kind of strategy. Okay, so this is what I had when I was at Louisiana Tech, and at Louisiana Tech it has very good micro fabrication facilities. So here you see, this is the image, this is the ACM image of these micro channels, and then you can see these are all 100 micron deep, okay, and this is 50 micron wide, and these are the channels, and this is based on silicon, because this is how the computer chips are made by the silicon, this thing. So we use that strategy. Now here, what we do, you actually try to put the catalyst and support all these in the channels. At the same time, you don't try to fill it up, otherwise you will defeat the purpose. And then you put the glass on it, apply a high voltage, and then you make a silicon-oxygen-silicon bond. So that's how you seal it. So that's what you get when you put it together, and that's the inlet for the gases, and then the outlet, and then of course you have a mass spectrometer, mass spectrometer, GCMS, and then you analyze this. Then you see, you can have so many channels, 116 channels and all this. Now when I move from silicon to stainless steel microreactor, it's going to be a little bit different, but just see this concept, and this is how you do it. So again, the fisotropes, you start with the CO and hydrogen, and you are making this methane and higher alkanes, and these are the typical catalysts, the iron, cobalt, and ruthenium, and these are the supports, alumina, silica, titania, all these. Now, why we actually do this? Because in industry, this is a big thing. Like Shell, Sasol, the South African company, Petroleum, and on all these, and these are all this, and this is ideal. And this is also called gas to liquid technology, because it is, you can't transport so much of gas, but if you liquefy it, then you can transport it easily. Okay, so that is also called GTL, gas to liquid technology, the catalyst development. And here you see, this is the work we did a long time ago at Louisiana Tech. I'm just giving you a little bit of history, and we actually started with this iron, cobalt, and ruthenium. Then when we added the ruthenium to the iron, cobalt, then you could really improve the conversion of CO, and then with and without ruthenium, we examined this, because I was very new. I was trying to figure out how to do these things. This is back in 2003, 2004, okay, in Louisiana. And then, these are the typical surface areas called the Viii surface areas, and these are the pole volumes. And then you can see the weight percent. We try to maintain 12 or intended loading, and then if you look at the stability of the catalyst. Why stability of the catalyst? Because if you're running your process, you need to make sure your catalyst is very stable. Otherwise, it's no good. Otherwise, you cannot really apply. So that's why you do the stability studies. And what we found, which is consistent with what is reported in literature, you see that the iron and cobalt, which is the workhorse in industry, they're very stable, and the ruthenium actually deactivates much faster. And as you know, ruthenium is very expensive. Okay, so this is what we did in Louisiana. But after I moved to North Carolina A&T as the chair of the chemistry department, I had a very difficult time to do research, because you're an administrator. You have to, you can't, those of you who have been in that position, you know what I mean. And so it was very difficult for 4.5 years. Then I gave up, and we were very fortunate to get the NSF Center. Using my previous research at Louisiana Tech, we built completely microfluidic lab. There was no clean room even at that time when I joined at North Carolina A&T. And now we have joint School of Nanoscience, all this. So this, and we did this. And when we started doing this NSF project, like one of my students, who was a chemical engineering student, he was telling me, Mahabub was telling me, Professor Kuila, have you looked at the effect of all these supports in individual metal, especially in microchannel microreactor? I said, no. I said, okay, you can do your thesis that way, and I'm going to make the story very short. So he went to the titania, sol gel, and what he found is exactly opposite of what I just showed you. I showed you that if you go in the silicon or silica sol gel, then this is what happens. Ruthenium deactivates very fast, right? But now, if you put titanium, everything is opposite. So you see here, ruthenium is more stable than the iron or the cobalt. And so we didn't understand why this is so for a while. And then we figured out that if you really look at the XRD of these materials, of these catalysts, that in the case of ruthenium, you actually have rutile phases. And these are absent in the, in the cobalt and the iron. And so this is how we can explain, because TiO2 it has a different there's different structures, rutile and all this, and silica you don't have. So that's why that has a prominent effect, a pronounced effect on the catalysis. So let me move on. So this is what it did. In the interest of time, I removed a lot of slides to make it to fit with the time. So why did we move from silicon microreactor to stainless steel microreactor, right? The reason is, for silicon microreactor, you need a clean room, okay? And then you have to invest a lot of money to have a clean room and all this. And then the other problem with the silicon channel system, it breaks very easily, okay? You can't reuse it. So that's why we moved into this 3D printed microreactor. By the way, because of time, I removed this ALD. ALD stands for atomic layer deposition. You can actually deposit catalyst specifically in the channels, and you can close it and read it. We actually published, and during the COVID time, we wrote a book chapter. It covers most of these in this reference. My PhD student, Nafizuddin Muhammad, he actually was the student who mainly, with my postdoc, Pari, they did this. And so anyway, so we moved into this stainless steel or 3D printed or 3D printing microreactor, and you see, you are going to lose the surface area quite a bit because the channels are 500 micron. And we use mesoporous materials like MCM41 and SBA15, where you can get a lot of surface area instead of sol gel that I told you. Okay? Now you see, so this is the main reason. So you see, you can enhance the reaction surface area, huge fabrication cost, all this, and then you can use this. And so if I move a little bit faster, and you see that no clean room is required. So you basically can just assemble this, and the 3D printing by stainless steel, and then you put this, and this is how you see when you coat the channels, okay, with the sol gel and all this, and then you can put the whole thing together, and you can reuse. Previously, silicon microreactor, you can't reuse it because you seal it, applying a high voltage between silicon and glass. So here, so this is Protolab, which is not very far from us, in Lale area, and so we did that. Now, we actually did a lot of studies at 1 atmosphere for the proof of the concept, because you don't just jump to the high pressure, because high pressure you are working with CO and hydrogen, so you have to be very careful when you do this. And so this is what we did, and you see this 1, 2, 3, and 4. So this is the numbering up. So if you go on increasing the numbers, what will happen? And so we did this, and you see that these are all the control experiments. So because a lot of times reviewers will ask you, because you are using stainless steel, have you run the blank experiment? And you can see that there is no effect. This is perfectly fine. So you do this. Now let me take you quickly through this. So this is cobalt ruthenium, and KIT6 is a mesoporous silica, just like SBA15 or MC41. And this is a Korean version, that's why it's called KIT. So here you can see all these images, SCM and TM images of this catalyst, and this is the surface area measurements, that you make the plot, the BT surface area, and This is actually, we did this during the COVID time. And so at the time, when we did this, we saw the first time the liquid. Because we had never seen the liquid, because we have been running these reactions at 1 atmosphere. But the moment you go to higher pressure, this is this tiny, like a lab on a chip idea, these reactors, and we could see these liquids, and we were very excited. The reason was we were working with NC State, those who are doing the reforming of the biogas, so you get the syngas, so we could do the on-site production of liquid fuels. And we did demonstrate that we could really do it. So here, because doing something in the lab and then doing it in a larger scale is a different challenge. And because I spent over 8 years at Hercules and Great Lakes Chemical, so I know how difficult, how challenging it is, where the rubber meets the road, okay? So here you see, when you do this, you can see all this. CO1 means methane, ethane, and all these, and then you can see the higher, the longer chain of the liquid fuels. So, and this catalyst, and this is left side is the atmospheric pressure, and the right hand side is the 20 bar, and you can see this. Okay, all right. Now you see, the inner surface bioenergy center was for more than 12 years. So the second phase, what we propose, that how we can utilize the CO2 with the syngas and convert into something more useful, maybe like olefins. And from olefins, you can make all kinds of products like hydroformylation, your shampoos, and all that, you can make. And so these are all these catalysts. And then again, as I said, we are really looking at the metal support interaction. Okay? And so this is like what is the active side? This is the support. And then, the carbide, because usually the Fischer-Tropsch reaction goes through the iron carbide. I didn't go through that. That's the mechanistic aspect when you do this kind of reaction. And so the whole objective, or one of the main objectives, I should rather say, that how you can make olefins. Because olefins should be good, because fuels is okay. That is nice, and it will be useful for gas technology. And you see, now you see that this is called CO and H2O. When they react, you can get the CO2 and hydrogen. And this is what happens when you do steam reforming. Okay? Now, the reverse water gas strip reaction is where if you start with CO2, then you convert this into the CO first. That's why it's called modified Fischer-Tropsch. And then the CO then reacts with the hydrogen to do this. So think about this. Yesterday you were listening about green hydrogen, right? If you have green hydrogen and you put it in, and you can make the fuels. So you can put a combined system, okay? All right. So now let's look at something, how we try to make some olefins. So this is one of my undergraduate, Saif Hassan. He actually started with this project, and because with my postdocs and the PhD students, and so we wanted to see what will happen if you use graphene oxide HSI instead of silica, alumina, all that I told you, right? And so our goal is really to make these olefins and the long chain hydrocarbons. And you see, this is how the catalyst looks. And what we are really trying to do, or I'm trying to show you here, graphene oxide and the iron is the catalyst. Then we use a promoter. What is promoter? It just promotes like manganese and sodium, these metals, and which basically makes the basicity higher. And how that will have on the conversion. So you see that now if you go, this is the manganese and sodium. This is the TM images, and then you see these are the typical surface area. Surface area is not that large here, okay? Not like these mesoporous materials. And you can see the average crystal size is like 20 to 30 nanometer, and these are with the promoters. And what you really have is the metal oxide, Fe3O4, or the manganese oxide. Now if you go here, yeah, now this is called the hydrogen TPR. What it stands for, temperature program reduction. Now why you do that? Because when you are trying to do any reaction, it is the reduced metal which is active. in the Fischer-Tropsch synthesis. So if you use the hydrogen, you can reduce it the metallic form, which actually forms the carbide with the CO, and that is the active species for catalysis. So you do this just to see how this is going to be, what temperature you should use or prepare your catalyst, the final species. Okay. So if you look at this here, you can see that the iron graphene oxide, the black one, you see the temperature is 819. But the moment you have the promoter, like manganese, it moves way over here. Okay? And then if you have manganese and sodium, the blue one, you can see this. So what are these peaks? Because you have this Fe3O4, right? Means which is a mixed oxide, FeO and Fe2O3, and you reduce each of those. Okay? And that is the active species for catalysis. And you see that this is, of course, you look at the shapes, rod type, and all these kinds of things. We didn't delve into this because there's another thing that one can look at. There's morphology of the catalyst. Okay? So once you do that, then you try to do the reactions, and what he found with the addition of the promoters, you can see that as you add the promoter with the manganese, sodium, that the CO conversion goes way up, above 90%. So this is really, really high. And then if you look at the selectivity of the products, and then you can see the propene, C3H6. See that this goes up. So we were very happy that we could generate the olefin, because this is proof of the concept, right? And so we got this, and in the interest of time, I'll just go through this quickly. And again, you do the stability. 5 more minutes? Okay. Yeah, and so you see here, manganese sodium, this is the conversion goes up, and then this is the iron graphene oxide, and you can really move through this, and then you can see the other products, the selectivity to the C4 plus. The C4 plus means all the other higher hydrocarbons. So those go up with the promoters, as you can see with the manganese sodium, this thing, and then this is again, I'm back to this cobalt ruthenium KIT6. Here we are focusing not pure syngas, CO and CO2. So because you have to know what you can do with the CO2, and you can see with these different ratios, again you can make these liquids. And this is the feature article in the RSC journal this year that got, that's the picture, like simple picture, CO2, hydrogen coming, then you have the product. All right? So now, I'm not going to go through all these details. What we found that if you use 1 to 1 to 2, this ratio, that is the best result. And as you increase the temperature, you get these longer chain hydrocarbons, and then in the Water-gas shift reaction, it increases the amount of CO2. So it's a competing reaction. We are also producing some CO2. So this is what this is. Now, the last, I can have 5 minutes. I'll just go through this. So I will now switch to, and I skipped the CO2 capture, okay? I'm just a conversion. We are going to look into electrochemical reduction. Because if you once you capture, what do you do? You have to convert it into something useful, right? So those of you who are in this area, if not, there are many ways. Thermochemical, that's what I just showed you, up to the last slide. You can have also photochemical process, and then electrochemical. So I'm going to focus on the electrochemical, and these are the typical metals that are used, copper, zinc, and all this. And we focus on the copper palladium. Copper is the, as you know, if you have heard the literature, copper is the main element, the main catalyst in electrochemical reduction. And we wanted to understand if we make copper palladium bimetallic, what will happen? Okay, the materials of interest, and then you see, we try to make copper palladium 1 to 1, copper palladium 3 to 1, and then the CO2 reduction, you can make formic acid or formate, you can make acetic acid, and you can make methanol. So all these products, depending on how this is a paper that we published in collaboration with Caltech, Professor Bill Goddard's group, and so this was published this year. And so we looked at these three ratios to see the effect of these ratios. Okay, so let me move on. And so here I show you the XPS, X-ray photoelectron results of this 1-to-1 and the 2-to-1 and 3-to-1, and you can see it's an alloy formation. Then you can see these peaks, and then XRD peaks actually move a little bit because of this alloy. It's not exactly at the same point. Okay? That is good. That's how we know that you are forming the alloy. And then you can look at the TEM image. This is called the field emission TEM image of this histogram of the particle size, and you can see a shift of the peaks to the lower angle due to this crystalline lattice structure. Okay, now so here is this again all these images. This is the atomic percentage of these. This is the EDX elemental, the EDX analysis for this, and here is the main part. Those of you who are not familiar, this is called cyclic voltammetry, where you plot the current versus the potential, and then you see this. And this right-hand side, what you see is called the chronoamperometry. What it means is you plot the current with the time, and then you can see how all these are behaving. In other words, you change the potential, and then try to see how this. And this is with different ratios of copper and palladium, 1-to-1, 1-3, and 2-1. Then what you see, you analyze the products using NMR. Okay, and what you see that when you use 1-to-1, you only get format, very selective. And we did not see hydrogen production, because hydrogen production is the major issue where the paradigm efficiency decreases. So this was really, really exciting for us. We actually have filed patent application, okay, on some of these. And then you can see, if you go to 3-to-1, you can make not only format, methanol and acetate. So you can get different products depending on the ratio of the copper to palladium ratio, and then you can get these different products as you can see. All right. So Professor Goddard's group at Caltech, they actually did their theory to understand how we are getting all these different products, and what you can see that format, when you have 1-to-1, you have a path like that 1.4, and then this is all at pH 6.8 for copper, and then when you go to 3:1, then you can see that you have a different path, and this HCOH then it goes to methanol, okay, and then you can get also acetic acid. So that's the other product. So the path changes depending on this copper palladium ratio. Okay, so this is the paradigm efficiency, because you want to see your energy properly. So this is just the same thing. I just wrote a bigger scale thing. So let me now summarize what I have told you. So I first told you about isotope synthesis using 3D printed stainless microreactor. I took you quickly through the silicon-based microreactor, how we moved into this. And in the silica sol gel, the cobalt and iron are better than ruthenium. And then if you go to TiO2, everything changes, right? And then you can use a promoter like manganese or manganese sodium, add it to the iron, and then you can see the propene selectivity increases. Okay, and then I was also told you about CO2 mixture. You can go to longer chain hydrocarbons due to enhanced growth and reduced methane formation. And then the electrochemical part, the last part I just presented. So we said that if you use 3:1, then you can get methanol, acetate, and format. But if you use 1-to-1, you can selectively just make the format. But 2:1 actually, they give you both format and acetate. and we could suppress the hydrogen evolution. That is significant for us. And these are all verified by quantum mechanical calculations at Caltech. And so this is the picture during the COVID time. Like I used to use 2 masks. If I'm coming closer, when I was teaching, I will use 1 mask because I was a little bit away from the students. And this is the pre-company executive, and I think Lawrence Livermore National Lab, Jeremy Kim. These are the fundings, NSF, CENIC, and UNCRY. This is Chapel Hill and Mississippi. And these are the students at the postdoc, some of them on that time. And then this is my more recent group from last year, having all these different kinds of research areas. And then undergraduate I mentioned, this is my undergraduate, I'll show you, Saif, and he actually did that work on the graphene oxide. And I think I need to thank the organizers. I need to really thank Dr. Judy Jadhav, because I did not know that he was involved in the Chemical Society. And so when I met him at San Diego, he was telling me, oh, you should consider this, or you should do this. And so that's how I'm here. I'm very happy because I'm back to Chennai. I mean, Madras, we used to call when I was a student. And I'll be very happy to answer any questions. I'll be happy to entertain other areas of research as well. Thank you so much. Thank you so much, MCC, for inviting me.
Thank you, sir. Thank you so much for highlighting the CO2 conversion into fuels, and whatever we are doing, it should end up with a value-added one. You have beautifully quoted, and a variety of catalysts you have highlighted. Especially for the beginners, it will be a boon. Thank you, sir. On behalf of the organizing committee, please join with me in honoring our speaker. Thank you all.
Thank you, sir, for your wonderful presentation, and thanks to Dr. Swarnalatha for chairing the session. Now we will break for track-wise sessions. In that first, there will be oral presentation. After that, we will have invited lectures, then poster presentations in exam gallery. Then 11:30, tea will be served in the examination office for the participants and the students, and for the delegates, chairpersons and faculty members in Innovation Park. We all request the students and participants to have the refreshments in exam office, visit posters in the exam gallery, and take selfie at the selfie points to create some core memories. Lunch will be served in the canteen for students and participants, and in MMIP for delegates and faculty at 1 p.m. We will assemble here again for valedictory at 2 p.m. sharp. Have a great day. In the sidewise, we have projected the revised schedule. Thank you so much.